Welcome to another exciting educational video brought to you by Vision Concept Academy. Today we'll be looking at the electric circuit in physics. We'll be discussing the components of electric circuits. We'll see the voltmeter, the ammeter, the variable resistor, and every other component making an electric circuit. We'll determine the connection of resistors, one of the components of the electric circuit, in series and in parallel. And we'll look at the Ohms Law. The Ohms Law defines the properties of both voltage and current of a given material. Then factors affecting electrical resistance. We'll look at electrical work done in a given circuit. It promises to be an exciting episode. Class, so sit tight. Make sure you subscribe to get more of our content, and you'll be glad you did. Okay, so here we see the components of the electric circuit connected. These lines are wires. And this is the ammeter. This is an ammeter. The ammeter measures the amount of current. This is the voltmeter. The voltmeter measures the amount of voltage. This is the resistor. R is the resistor. It provides a kind of resistance to the flow of current to actually appropriate the amount of current that will flow through a particular junction. And this is the cell or the battery that provides the electromotive force. The electromotive force to move the current through the circuit. This is the switch. At this mode, this switch is open. This switch is open at this mode, meaning that there's no contact. Once the switch is closed, the circuit is completed. So the battery releases the voltage. It's polarized at this point. This is the positive charge, positive terminal and negative terminal. So the current flows from here to this point. And you note that always the ammeter is connected in series to the battery or the source of voltage. Always note this is very important. The ammeter is always connected in series, and the voltmeter is always connected in parallel. So another component of this setup is the resistor. The resistor is a component which is specifically designed to provide a known resistance in the circuit. Okay, so standard resistors are those that have fixed resistor value. Also, the resistance value is measured in ohms. Resistance is measured in ohms. Is measured in ohms. This is a symbol for resistor. It's measured in ohms. You have other units. You have kilo ohms. You have milliohms for smaller ones. Kilo ohms is like times 10 to the power minus 10 to the power 3, and so on. So you have the fixed resistance that has the fixed. That's types. I'm looking at types now. You have the fixed resistance or resistor and the variable resistor. Variable talks about you able to select the amount of resistance that will be needed in a particular circuit, depending on how you want to limit the flow of current. So I'll just go into the different components in the electrical circuits, how it is measured, how it is denoted. When you see it in a circuit diagram, how to identify every component of the electric circuit. Okay, so we have all the components that you can see in an electric diagram or circuit. Here we have the cell. This is the cell. So the cell is just like a small voltage source. Then you have the DC source. If you see this symbol like this, it means it's a DC source, meaning that only direct current is produced. Now this is the resistor. Either you see it in this way or in this way. Like I said, resistance is measured in ohms. Now you have the switch. This is symbol for switch. This is the battery. The battery produces the voltage for the circuit. This is a variable resistor. These two symbols are for variable resistors, meaning that you can actually vary the amount of resistance at a particular time. Mostly for experimental purposes, you use it to vary the amount of current that will flow through. Like I said before, resistance or resistor is the component that opposes the flow of current and limits it, so it doesn't make it flow so much. So this is earth connection. Sometimes, or most of the times, your circuit needs to have a path that goes to the earth. You have cross connection. Two wires are connected across. They are not meeting at all, so that's why it's jumping. This one is jumping. They're not meeting at all, so it's a cross connection. This is the symbol for coil. So you have a coil. When we look at magnetic field, we look at what the role of the coil of wire plays in magnetic field. This is the transformer symbol that produces AC, that regulates AC, can change AC from one form to another, maybe from a higher form to a lower form. When it's stepping down, that means that the AC voltage is coming from a higher form and going to a lower form. If it's stepping up, the AC voltage is going from a lower form to a higher value. So we'll look at transformer later. Then this is the voltmeter. The voltmeter symbol for voltmeter is for measuring volts. This is the bulb, one of the components that where you have the output, where you have the effect of a voltage current coming in and the light showing. So electrical energy is converted to light energy in this component. You have the ammeter and the galvanometer. Okay, so we're moving on to how we can connect the resistance or resistors in parallel or in series. Okay, so next we're going to be seeing parallel and series connection of resistors in an electric circuit. So resistors are connected in series if you line them up in a daisy chain format like this. One into another, and so on. This kind of configuration or arrangement is known as series connection. So the characteristics of this kind of connection is that one resistor moved into another in a daisy chain form. So if I have three resistors or four resistors like this, R1, R2, R3, R4, where R is known as the resistor with resistances in ohms. Okay, the equivalence, comma, or the total, or the resultant resistance is given as simply R1 plus R2 plus R3 plus R4 plus whatever is continuous, as long as it's in this form. One is linked to another, this other is linked to this one is linked to this one, and so on. The end of the first one enters the beginning of the second one, the end of the second one enters the beginning of the third one, the end of the third one enters the beginning of the fourth one, and so on. So the total resistance or equivalent resistance or resultant resistance is given as R1, R2, R3, R4 plus. So if, for instance, this is 5 ohms, this is 2 ohms, this is 1 ohm, this is 7 ohm, the total resistance RT is given as 5 plus 2 plus 1 plus 7. That will give us 5 plus 2 is 7, 7 plus 1 is 8, 8 plus 7 is what? 15 ohms. That would be for that. So this is for series connection. So, but when you have the parallel connection, you see that the resistors are connected one on top the other, one on top the other, like this. So this is a junction. This is a junction here. So this is arrow 1, arrow 2, and arrow 3. This is for parallel. Let me put it by the side here. Parallel connection, parallel connection, connection. And for parallel connection, total resistance 1 over RT is equals to 1 over R1 plus 1 over R2 plus 1 over R3. So this is how you get it, where RT here is the resultant resistance, equivalent resistance, or total resistance. So you are going to complete this in algebraic form, fractional case, where you have to get the LCM and get the value of RT. We'll do a practical example on this. But the high point of this kind of connection is that this current that flows in through like this would, when it comes here, it splits into different components. Arrow 1, sorry, this I, let's call this current IA. When IA comes in here, it splits into 3 current components. Let's say I1, I2, I3. This effect is because the resistance here in each of these nodes is different. So this current that is coming in here will divide into 3 currents such that IA like this is equals to I1 plus I2 plus I3. That is, all this will form this. Understand? But what is divided, how it is being divided, depends on the resistance connected at these terminals. Remember, we said resistance limits current. So the more we'll talk about Ohm's law, and we'll see how this thing plays out. The more the resistance here, the lesser the current that will come here, because the higher resistance will limit current flow. Lower resistance will increase current flow, and so on and so forth. So for this situation where you have the series connection, it is same current that will flow through. Same current that will flow through. But for this case, different voltages, V1, V2, V3, V4. Different voltages, but same current. Here, different current, but same voltage. So I will have something like this. Please pardon me, it's becoming a little bit clumsy. I'll have this terminal connected like this, like this, like this. The same voltage will go across all this, but different current will go, across them. So note, if you have parallel connection, same voltage across all the resistance, different current across all the resistance for parallel connection. But for series connection, same current across each of the resistors and different voltages across the resistors. This is very typical of this kind of connection. Okay? So we have an example on the board here. It says if 3 resistors, 2 ohms, 3 ohms, and 5 ohms are connected in parallel in a circuit, calculate the equivalent resistance in the combination. So look at how it is being visualized like this. 1 here, 1 here, 1 here. So this is parallel connection, like I said in the previous discussion. Also, this first one here is 2 ohms, second one here is 3 ohms, and third one here is 5 ohms. So the resultant resistance is actually given in this formula: 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so where R1 is this, so I will just say 1 over RT, which is we are looking for RT here. 1 over R1 is 2 plus 1 over 3 plus 1 over 5. Okay, so at this point I will just get the LCM. 1 over R3 is equals to, so I will rule my line like this. So the LCM of 2, 3, and 5. 2, 3, and 5. What's the LCM of 2, 3, and 5? 2 times 3 is 6. 6 times 5 is 30. Okay, 2, 3, and 5, 2, 3, and 5. Okay, so 30 is the LCM. All right, so 2 into 30 is 10, 3 times is 15 times. 15 times 1 is 15 plus 3 into 30 is 10 times. 10 times 1 is 10 plus 5 into 30 is 6 times. 6 times 1 is 6. So I'm going to add up 1 over RT is equals to okay, 15 plus 10 is 15 plus 10 is 25. 25 plus 6 is 31. So I have it as 31 over 30. So when you flip it, you flip RT and 1, and you flip the other one is 30 over 31. This is the equivalent resistance. By the time you compute, you actually have it in 0.97 ohms. That's the answer. So it's as easy as we can see. Okay, so we have the Ohm's law. The Ohm's law states that the current I flowing through a metallic conductor is directly proportional to the potential difference across that conductor, provided that the the temperature and other physical conditions of the conductor are kept constant. So if you have this like this, that the current flowing through a metallic conductor, flowing through any form of conductor, is directly proportional to the potential difference across that conductor, provided that the temperature and every other physical condition is constant. By the time you remove this constant of proportionality and introduce this equal sign and a K times V, this K is known as the resistance. This K is known as the resistance. Okay. Sorry. Okay, so removing the constant for proportionality, we know that R, which is equals to V. Where I is the current, R is the resistance, which is the constant, and V is equals to the voltage, okay, or the volts. So this can actually be determined in the laboratory using the cell, using your cell and the variable resistance to measure the different kinds of voltage. So if you have this kind of connection, you have your cell here, you have your ammeter here supplying the current, then you have the variable resistor here, okay, supplying the resistance. So you put a voltmeter here to measure it. Remember all the symbols that we drew, and there's a switch here. So when the switch is closed, current will start flowing. Now this is what we can use to determine the what's it called, the resistance of this material here. So if this switch is closed and current is flowing, I is flowing here, and then it comes here, the voltage is measured at this point. If you vary the resistance across this material, you get different readings. So you have, for first instance, let's just do a table because it's an experiment. Let's do a table like this. Okay, so you have, for the first instance, you have I1. At I1, you will get a V1. At I2, you will get a V2. That is the current that is you are changing the current because of the voltage you are, meaning the resistance you are varying. We said that the resistance is the opposition to flow of current. So if the opposition is less, you have more current. If the opposition is increasing, the current will continue to increase. So that's what happens. So you have I2, I3 here, and you have a corresponding value for V3. You have I4, you have a corresponding value for V4. You have I5, and you have a corresponding value for V5. Then let's say I6, corresponding value for V6. So if you plot the graph of voltage and current it goes like this. This is voltage axis, V measured in V, and this is current axis measured in amperes. So as it is increasing, you have a straight line like this. So the relationship between the current and the voltage is a straight line graph, and this slope of the graph will give me the resistance of that material. So we will stop here for today. I hope this video has been informative for you, and I'd like to thank you for viewing. Kindly subscribe to our channel to get more educational content, and share to friends so that they can also enjoy what you're enjoying.